Hello and welcome to another video brought to you by HPart. Today we will discuss coupling collimated light into an optical fiber. In this video we'll be using Fresnel. Fresnel is free, general-purpose optical design software available at h-part.com. To get started, let's open the Revolution panel. And go ahead and select the PCX preset. We're going to leave the radius of curvature and diameter as they are. Go ahead and create our lens. So now we have our first lens. The next thing we need is some light. To that end, we're going to open the emission panel. And we're going to select a uniform infinite emission. We can see that the target has already been selected as our lens, and we're using wavelength from 400 to 700 nanometers. This will be good for our purposes. I'm going to go ahead and create that emission. Now that I've created it, I'm going to cast the rays. Now this looks like a lot, but let's zoom out and take a look at it. The first thing that we notice is that the light is starting at the right and heading to the left. This is not what we want. Usually, in an optical system, we design it so the light starts at the negative z-axis and it heads down the positive z-axis. So to make that happen, we're going to open up our uniform infinite emission panel again, and we're going to flip the target normal. Then we're going to recast the light again. Now this has flipped it, so it's going the right way. But there's still a lot of rays being rendered, and it's difficult to see what's going on. So the next thing we're going to do is we're going to open up our display panel, and we're going to enable section view. Section view is only going to render rays of light that have an x-coordinate between plus or minus -1, at least in this setting. Now this is much clearer. We can see the rays of light starting at the left and heading towards our lens on the right. When these rays hit the lens, we can see that a lot are getting totally internally reflected. Many of them are actually focusing backwards. A fair number are focusing at a very short distance from the lens. These are the rays that got internally reflected. And then there's a bunch of light that's heading out to the actual focal point of the lens. So now that we have the light, we have the lens, we need to create a detector, which is where we'll seat the fiber. I'm going to go ahead and open the detector panel, and I'm going to create a detector at 50. I'm going to rotate it 180 degrees so it's facing the lens, and I'm going to trim its dimensions down a little bit so it better fits the size of the lens we're using. So now I've gone ahead and I've created my detector. Now let's take a look here. To put a fiber into our detector, we need to create something called a detection. A detector doesn't do anything until you couple it with a detection, even if the detection is empty. But usually, you have gates associated with the detection. Maybe the gates might be the rectangular boundary of your imaging sensor. In our case, it'll be the circular boundary of our fiber. And we'll do one other thing. We're also going to add a numerical aperture gate. This is going to prevent light from being marked as detected unless it has a numerical aperture less than or equal to 0.22. Now, 400 micron fiber with a 0.22 numerical aperture is very common in spectroscopy. So let's go ahead and create that detection. Now that we've created the detection, we're going to zoom in on the detector. We're going to have to zoom a little bit in, but here we go. This is our 400 micron fiber. This is where we're trying to launch the light into. Okay. So now that we've created our detector and our detection, we're going to cast the light again. And we'll notice that some things have changed. The light has extended. It's now traveling, hitting the detector, and then exiting out the back. We can also see that the focal point of our light is behind the detector, and most of it is most likely missing our fiber. But before we can make this better, we have to quantify how poorly we are doing. And to that end, we're going to create an analysis. The analysis we want is collection efficiency, which is the ratio of detected to emitted rays. So let's go ahead and create this analysis. I'm going to mark it for detections only, and I'm going to set it to filter stray rays. Now we haven't configured any light paths yet, so stray ray filtering isn't going to do anything, but we'll get it set up now so we have it later. Now let's go ahead and run the analysis. Now what we notice is we're launching about 5 million units of intensity. Most of those units of intensity are hitting our detector, but a very small number of them, only 0.091%, are actually making it into the fiber. And here is where they're hitting inside the fiber. As you can see, we're not doing a very good job. So now that we've created our analysis, we're getting closer to being ready to actually optimize it. But before we do that, it'll be very helpful if we define what light is stray and what light is not. When you're running an optimization, it's good to be just focused on exactly what you care about. And initially, it's not the stray light, which can confuse the optimizer. And so to that end, we're going to create a light path. We're going to open the panel, and we're going to use this tool to pick the surfaces that are in our light path. A light path is just the path light travels to be considered not stray. Any light that doesn't meet this light path, that doesn't start at the left segment, head to the right segment, and go to the detector, will be considered stray. So now that we've created our light path, I'm going to drag it up here, and we're going to go into our emitter, our emission. And we're going to add this light path as an intended light path for our light. And now we're going to cast our emission again. Now you'll notice nothing happened. This is because we're currently displaying all of the stray and all of the intended rays. So I'm going to open up the display and I'm going to say hide stray rays. And now you'll notice that we're only seeing the rays that follow our light path, which is what we want. And now we no longer have the warning for our analysis. So good, we're getting closer to being ready to optimize. But before we actually create a merit function and fire up the optimizer, we want to do one more thing. And that is we want to create an analytical model of our optical system. Now we don't need to create a full model, but we should put out the minimum number of equations to roughly know what our system is doing and to get it in a roughly correct space for analysis. This is a very simple optical system, so we could forego this step. But it's a best practice, and so we're going to do it here just to demonstrate. To create a rough analytical model, I'm going to open up a note panel. Notes in Fresnel are a lot like workbooks in Mathematica or Jupyter, if you're familiar with those. And we're going to start by just working out some basic equations to know the rough radius of curvature our lens should have and roughly where our detector should be for our fiber. These are going to be paraxial approximations, which means they're only going to be accurate for light that's near the optical axis. This is the z-axis in our design. So we're going to start with some basic information. The first is the numerical aperture of our fiber. From that, we're going to calculate the half angle, which is going to be the arcsine of the numerical aperture. And I want to see that in degrees. Notebooks in Fresnel are unit aware, which can be a real blessing when you're working through a complicated design. So you might be quibbling with me and saying that I neglected the index of refraction on my numerical aperture calculation. You'd be correct, but we're in air, and so the index of refraction is roughly 1, so we can ignore it. Now, the half angle of our fiber is about 12.7 degrees. That means that any light that comes in at a steeper angle than 12.7 degrees is going to get rejected by the fiber. We want to put the detector far enough away from the lens such that when light comes in through the top of the lens, it's going to hit the fiber at roughly a 12.7 degree angle. Anything steeper, and we're just wasting light. And anything farther out, we're making a lens tube that's going to be longer than it has to be. Okay, so now the question is, what should this be? Well, the diameter of our lens is 25 millimeters. And so to get this length here, we just need to do some basic trig. So to that end, we're going to have our focal length is equal to d over 2, which is the height right up in here, divided by the arctan of the half angle. And with any luck, it's going to be the tangent of the arc angle. All right, so now we have our focal length of 55.4 millimeters. The other design parameter that we'd like to get a rough handle on is going to be the radius of curvature of our lens. So to that end, we're going to use the lensmaker's equation. So our index of refraction for the lens is going to be 1.518, which is the index of refraction for N-BK7, which is the default material in Fresnel and the material this lens is made out of. Now we could have selected a different material by opening up this panel and picking a different one from the drop-down, but we're just going to leave it with N-BK7 for now. I'm going to go ahead and subtract 1 from this, and then I'm going to multiply it by the focal length. That's going to give me a radius of curvature for the lens of about 28.7 millimeters. Okay, so now that I know these two parameters, I'm going to input them into our system so that we start in a good position. First is our radius of curvature, which is going to be 28.71 millimeters. You can notice the curvature of our lens got a lot steeper. And then we're going to set the distance. Okay, so we're going to open up our detector and we're going to change its position to 55.426 millimeters. So now we should be in a reasonably good position. Let's take a look. Okay, well this is looking a lot better, but it's a little hard to tell because of this double cone here. And we're going to talk a lot more about this cone later on and in subsequent videos. But for now, it's sufficient to know that the actual paraxial focus is traveling right along here and hitting right in our fiber. We can see that by running our collection efficiency analysis one more time. And as we can tell, our collection efficiency has gone up quite a bit. We were initially at 0.09, and now we've risen up to about 24%, which is remarkably higher, and that's just with the paraxial calculation. But we can do a lot better if we actually run the optimizer with a proper simulation. And that's what we're going to do. First thing we need to do to run the optimizer is to create a merit function. A merit function is simply a function that combines multiple analyses to output a single number. And that number is what we want to minimize. Yes, it is a little confusing that we're trying to minimize a merit, but it's the standard terminology in the field, so we're adopting it here. So let's go ahead and add our first analysis. We've got a lot of options, but the one we want is the soft efficiency. Soft efficiency is a smooth version of the scaled efficiency metric, and smooth metrics tend to be much easier to optimize. Let's go ahead and add that. Now you see we have some options here. The first one we want to set is the target. That's what perfection looks like. A collection efficiency of 100% would be perfect. The next and arguably the most important value to set is the threshold. The threshold you could think of as what is good enough. In our case, we're already at 25%, so I think 50% is good enough. The distance between the target and the threshold is what is used to normalize the error for each merit term. And having normalized errors for each term, for each contributor to the merit function, is crucial for a good analysis. Then the final option is the weight contribution. This you should not use to normalize error, i.e. to make them all have roughly the same size. However, this is what you should use to tell the optimizer, hey, I care much more about this analysis than I do about another one. And since we only have one, we're just going to leave it at 1 for now. The next thing we want to set are the optimization variables. In our case, we're just going to vary the radius of curvature of the lens and the distance between the lens and the detector. So let's go ahead and search for this. The first thing is our detector position. So we've got that in there. And then the radius of curvature of the lens. So now we'll see that it's showing up as the values that we entered from our paraxial calculations over here. And the next thing we're going to do is we're going to put bounds on these values. Now this is a very important thing to do. When you run an optimization, you should almost always bound all of your values, even if it's just a guess. Because if you don't bound them, you will frequently be surprised to find that the optimizer pulls one of your values out to infinity or to 0, almost never what you want. So we're going to start with putting some reasonably tight bounds on these two values. Also, another reason to bound them, and this is very important, is that it dramatically shrinks the solution space the optimizer has to search over. And this increases the probability that you're going to find a global optimum, or at least a sufficiently good one. Okay, we've now completed the merit function. So now we're going to create it. And then we'll go ahead and hit the calculate button. Now you can see that we've got our value, which is about 25% right now, which is again a little different from the scaled value in the collection efficiency panel because this is a smooth value. And we can see that we don't have any penalties from our optimization variables. I'm going to go ahead and close this. The next thing, and the moment we've all been waiting for, is creating the optimizer. We're going to leave the algorithm selection as is. The default algorithm is CMAES, which strikes a good balance between exploration and exploitation. It's also very robust against poorly formed merit functions, so it tends to find a local minimum if it's anywhere near it. And then we're going to select the merit function that we've got. For the trace algorithm, because we created a light path, we can use the sequential optimizer. Whenever you can use a sequential ray tracer, you should. All this means is that the ray tracer is only going to pay attention to the intersections of the surfaces, or with the surfaces that are in your light path, in the order that they are in the light path. Without a light path, the ray tracer has to manually follow each ray and figure out which surface it's going to hit next, and that takes a lot of time. So if you already know the light path and you already know the sequence of surfaces that you care about, using sequential optimization will run much faster and will get you a better result in less time. So let's go ahead and create our optimizer, and we'll run it. So as you can see, it's starting to move the panel to reduce the merit function. And now it's stopped due to reaching the evaluation limit. You can see the merit function has dropped considerably from where we started and is more or less flatlined at this point. So let's take a look at our collection efficiency. Remember, before we started the optimizer, we were around 24 to 25%. So now we're going to run it. You can see that it shot up to about 43.7%, nearly doubling in a short period of time. You can also note, though, that the cone, that double cone that was causing issues earlier, has gotten substantially smaller. We're going to talk a lot about what that is and what it means in future videos. But for now, we're going to leave the work we've done as is. Now you might be saying 43.7% isn't a very high number. It's not a very good result. Since 91% of the light is hitting the detector, theoretically we could do a lot better than this, and that's true. But the real question you should be asking is, what collection efficiency does my application need? Because we can increase this number, but to do so, we are going to have to increase the cost and the complexity of the design. You can waste a tremendous amount of time and a tremendous amount of money making an optical system better than it needs to be. So whenever you start an optical design, you should first think, what performance do I actually need to succeed in my application? Now, for many applications, a lot of spectroscopy, for instance, 43% is more than good enough. But there are many other applications where you need to image something very quickly that you need to get the maximum amount of light into your fiber possible, and you're willing to pay the price for the increased performance. Now that's all for this video. In subsequent videos, we're going to dive into the details of how to increase the performance of this system. And we're going to thoroughly understand the different aberrations that are decreasing the performance of the system now. Thank you very much for watching, and I'll see you next time.